overview. So I am Andrei Mihai, and I will talk about our work into predicting weather radar data using an ensemble of neural network models. Okay, so the goal or the domain of this problem is weather nowcasting, so which is usually defined as weather forecasting for the next 0 to 6 hours, so short to very short weather forecasting. And for this work, we worked on the very short part, so less than 1 hour forecasting. And in our case, we used radar data. So the models that we created use radar data as an input and also output radar data. Basically, they are trying to make predictions of future radar data. This is the goal of what we want to do. Okay, so the radar data that we have is provided, it's real radar data provided by the Romanian National Meteorological Administration. It was collected over central Romania by a single polarization radar, this type of radar here. This type of radar creates a full volume scan every 5.5 minutes. So full volume scan means that it generates data about multiple different products at multiple different elevations, so different height above the ground. So for the work that we did, we used the reflectivity product on 6 elevations that we were told are the most relevant elevations. So the reflectivity product is actually one of the most relevant products for weather forecasting, weather nowcasting. So reflectivity suggests the location, intensity, and type of precipitation, the storm structure and size, and also the distribution of water particles in the air. So it's a very relevant product. So the data set we have has been collected from in 3 years, from 2020, 2021, 2022, and was manually curated by meteorologists. So it's not all the data collected by the radar then, but data for 264 days. So since the radar gets data once every 5.5 minutes, more or less, there are around 257 time steps per day. So we have 68,000 time steps in total. So at each timestamp, the radar gathers data for 230 kilometers around itself in a radius. And this data is represented as a data grid, a 460 by 460 data grid. So we have one such grid for every timestamp for every elevation. So more details about data representation. For example, here is a data grid, and how this works is that the radar would be in the center, and then here each cell represents a location, a physical location. So the cells around the center would be the ones near the radar, and then further away, and so on. And these are the values of reflectivity. And these 3 matrices would all be for one timestamp, since each represents a different elevation. So closer to the ground and then higher up, and so on. So more exactly, we have for each timestamp, we have 6 elevations. So R01 means reflectivity at the elevation 1, and the elevation 2, 3, 4, 6, and 7. These are the ones that we use. So we have these 6 matrices for one timestamp, and then for the next timestamp, again, we have a set of these 6 matrices, and so on. And in total, we have almost 68,000 timestamps, each with this data. So this is our data set. Now, what do we want to do? So this is a high overview of what the SepConv model does. So we want to use real data from 5 timestamps. So if the current time is t, we will use also the data that we have now and other 4 timestamps, previous time steps. Okay, and we want to predict up to 8 time steps ahead. So from 5 minutes to nearly 45 minutes into the future. So this is kind of the goal of what the model does. So how does it do it? So this SepConv-ens model contains 3 base models. So ENS comes from ensemble. We have an ensemble of 3 neural network models. And all of the models are the same architecturally. So the concept is that they use 4 previous timestamps. So t minus 1, t minus 2, t minus 3, and predict some time step into the future. The difference between these 3 models is what time step into the future they predict. Okay. So they will predict. We have 3 models, 1, 3, and 5, named after the time step into the future they predict: t plus 1, t plus 3, and t plus 5. Okay. As I said, each of these models have the same architecture. So this is the network architecture. It's a bit weird here because there is not a lot of space, but I'll try to explain it. This is the network architecture for one of the base models. All 3 of them have the same architecture. So there are 4 input layers, 1 for each time step, and there is 1 output layer, right? Because each network predicts 1 time step ahead. So the difference is that if here the output was given as t plus 1, t plus 3, or t plus 5, this is the difference between all the 3 models. So in the beginning, for each time step, we do a separable convolution separately for each time step so that the network learns some relevant features specific to that time step. And after this, we concatenate all these features into one bigger list of features. And from there, it will start to learn all the interactions within all the time steps in multiple layers. So, well, this is a bit longer. You can see here that these are 4 layers of this kind and 4 layers of this kind. So this is the idea. Another idea that you might see is that we did not reduce the size. So this was one of the innovation of this model, that the size always stayed the same, since the input and the output must be the same. The size stayed the same. So basically the kernel of the neural network just learns for each cell. But yeah, that's kind of the idea. Okay, so we have 3 models. How do you use these 3 models to predict 8 time steps into the future? So we separated this into parts. So first, we predict the data for t plus 1 up to t plus 4 in based on the real data, and then we use this prediction to predict the next part. So as you can see here, each model only uses 4 previous time steps. But as I said in the beginning, we want to use 5 previous time steps. And that comes into play, for example, here, when predicting t plus 2 or t plus 4. We use starting from t minus 4. So basically, we skip over the current data. We just take one data previously to predict t plus 2. Since we don't have something that directly predicts t plus 2, we will use the model that predicts 3 steps ahead to predict 2 steps ahead if you just skip the current step. So that's why we use, in total, the 3 models, so SepConv-ens, will use 5 previous time steps, because some of the base model will be used with the t minus 4 to t minus 1. So here, and also to predict t plus 4, we also use the model that predicts 5 time steps ahead, but we're skipping the current, the one in the current time, we're skipping t. So this is how we create the predictions for t plus 1 until t plus 4. And then for the next 4 predictions, we will use the previous predicted data to create them. So the predictions were done in a very similar way. So as you see here, we have used model 1, 3, 3, and 5. And then again, we used exactly the same model 1, 3, 3, and 5. So to predict data at time step t plus 5, we use all the predicted data and model 1. And sometimes we used also the real data just the real data from the current time step. So sometimes we skipped over t+4. So this is very similar to how this was organized. Sometimes we skipped over t and used t-4 when combining from 1 to 4. And then when combining from 5 to 8, sometimes we used t and skipped t+4. So this is the general idea on how the models are combined. The predictions from previous models are used to predict future data. Okay, so now that I've shown you what the model is and how the predictions work. In order to train it, we need to have the training data, and we also need to have the testing data to make sure to measure it. We also used a validation data set that was used using during training, but the data in the validation data set wasn't given to the neural networks to train, but after each epoch, after a network finished learning for one epoch, the validation was it was measured on the validation data set. And then depending on the result of the measurements on the validation data set, maybe the learning rate would have been changed. So that's the purpose of the validation data set in our experiments. So we have 10% testing, 10% validation, and 80% for training. Also, I wanted to mention that all three base models were trained with the same dataset. So we didn't split the data in different ways for each model, obviously. But we also did a split on a day-by-day basis because we wanted to make sure that the results are robust. So we don't use like the first 2 years for training. So from 2020 and 2021, the days from those 2 years for training and the years for 2022 for testing, because that wouldn't have been correct since, climate and everything might change a bit between the years, so it wouldn't have worked. So in order to make sure that the training is relevant for the entire data set and the testing is also relevant for the entire data set, we actually made the split on every day. So on all 264 days that we have, we split them in 4 equal parts of around 6 hours each. And then each of those parts was split into testing, validation, and training. So that means that both training and testing are from all of the days and all of the parts of the days, both nights and day and morning and evening and all of the days. So that makes the training much more robust. And yeah, the final datasets would be just concatenating all of these smaller datasets from each day. And obviously, we made sure that we wouldn't try to use time tests from here to predict from there. So it was done logically. Okay, and after that, we trained it. In order to evaluate, we used some metrics. We used some regression metrics, root mean squared error, or R2 score, which is more of statistical measure, but it's also used in computer science. We also used some classification metrics, while our model is a regression model. It predicts values. Classification is often used to measure the accuracy and to measure the how good a model is in weather nowcasting and weather forecasting in general. And actually, this critical success index and high scale score are scores made for weather forecasting. Yeah. We also used some image processing metrics since basically the matrices at every time step we have a matrix with several products, so it's like an image with multiple channels, and these two were shown to be actually quite useful. We did previous experiments some time ago, and we shown that for the experts these were actually pretty relevant. So we also used these two metrics. All right, so some results. So first of all, we have some results here for some example time steps 1, 3, 5, and 8 steps ahead. Yeah, and you can see here the root mean squared error. And so these are the regression metrics, the classification metrics, and visual and the image processing metrics. So first of all, you can see that we used for all and non-zero. So what does this mean? Is that we also considered measuring or computing these measures only for cells that are non-zero in the ground truth. So that is because when forecasting and nowcasting, it's much more relevant where the rain and where the convective event and storms, where they are, not where they aren't. And there are much more, it's a much larger area without any events than with events. So in general, events are much more relevant. So we thought that only measuring how well the events are predicted is a more relevant metric. And as you can see, actually on non-zero, the metrics are worse in general. And that shows us that it's much easier to just predict events where there are no events, where there are no events, but it's much harder to actually predict the storms and weather and how it behaves. Yeah, and also for these classification metrics, we use the thresholds 10, 20, and 40. So these are just basically what we said is, did it predict correctly that in this place it should be above 10 or below 10? So that's kind of how we transform from regression to classification. And we measure this classification and you see that as the threshold increases worse and worse, so that means that it is harder and harder to properly predict reflectivity values as they are higher. So in the more important or worse events, worse storms, what I mean. Okay. We also have some other results. We compared our model with a different combination. So we didn't, because of the long time that it takes to train these models, we couldn't do a proper search for the proper combinations, but we thought about what would be the best combination, and we compared it with some other combinations that we thought about. For example, this one where we have prediction at t+3 that was combined in a different way, t+5 and t+8. So we did some combination in a different way, and for our model, the results are better in general, in most of them, than the other combinations. Also, here are some visualizations. So here is a visualizations of the data for different radar products and time step 1, 5, and 8, observation and prediction. As you can see, as it goes further into the future, the quality degrades, but it is still recognizable. So it is still relevant into the future. And yeah, here is a different kind of visualization that is used from NMA side. And yeah, this also shows the kind of visualization that they can have access to using this model. Yes, and that is about it. Thank you. Any questions?